Okay, in this video, we have the normal and osculating planes of a curve. So if we have a curve R of t and a particular point here, the plane where the curve crosses perfectly perpendicular to the plane. In other words, if you were to draw a tangent to the curve straight out, that tangent would be perfectly perpendicular to the plane. That plane is called the normal plane. Normal plane. This is a little confusing because in the previous video, we spoke about the normal vector. Here it is from the previous video. And so this is the normal vector, and the normal vector does belong to the normal plane, but there's also the binormal vector. So we're using normal in two different ways, for the vector and for this plane. Just be aware that we're using normal as an adjective of a vector, which is this one, versus normal plane, which is this plane. So just be aware of that. It is a little confusing, but you will figure that out. And then we have the osculating plane. The osculating plane is a little harder to describe on a picture. Let me show you. This is a curve, some kind of twisted wire. So this is a curve, just like any old curve. And if you look at a curve at any given place, it will look like, if you close this enough, it will look like the sector of or an arc of a circle. It doesn't matter where you put it. If you just place your fingers correctly, it will look like a sector of a circle. I have a slinky here, and this is even more obvious or more clear. Okay, let me stretch this a little bit. So if you look again at any given point, so I'm going to focus here on this point, it would look like a circle. This is not a circle, by the way, because as you go in one direction, the curve goes up, and in the other direction, the curve goes down. Well, to the right and left, not up and down in this case, but it goes in different. So you cannot, just like this one cannot be placed in a plane. Doesn't matter how you put it. You cannot put it on a plane. It won't lay flat, no matter what. Any short section of this will be the same way. It may look like it can be put on a flat surface, but it doesn't. If you cut this correctly, and if it keeps its bend, it won't be able to go on a flat surface, just like this one doesn't. This one won't go on, no matter how you put it, it won't be flat. Same thing, if you cut this, it won't be flat. However, if you cut really close, it may look like it is flat. Although the parts that go off the flatness will be very, very small. In fact, you can probably stretch it out to cut here and it looks almost flat. You can, for sure, if you do a whole revolution, you will realize that this is not flat at all. But if you cut it at a very, very short segment, you will realize, well, it may look like we can place this little bit on a flat surface. That flat surface that we could place a little segment of the part of the curve is what we call the osculating plane. So there's a curve. Now this curve may be bending towards us, away from us. It's not necessarily flat, just like this guy is not flat. So pretend you got just a portion of it somehow. And even if I twist it enough there, it doesn't matter where, even if you just take a portion of it, it won't lay flat anywhere. It shouldn't, if it is a curve that is twisting in all three different directions. However, there is a plane, given one point, if you fix one point, there's a plane at which the curve, if this cut is small enough, the curve may seem like it is on a flat surface. You can always do that. You can find the plane at which, at this point, the surface is as flat, rather the curve seems to belong as much as possible to this. something similar happens to a tangent line. So in 2D, okay, so the osculating plane is similar to the tangent line in 2D. If you have a curve, this is in 2D. Okay, so why is this tangent? Okay, and a lot of people say, well, because it hits only at one point, and that is not necessarily true. The reason why we call that this the tangent line at this point is because if you zoom close enough, those two, the curve and the line, are very much the same. If you zoom even closer, the pixels should be big enough so that you cannot even tell the difference. Yeah, and some people say, well, the tangent is the line that touches at one point without crossing it. And that is not true, because if you have an S curve, yeah, we can have a tangent that crosses, well, it could be somewhere in there. But what is a tangent? Again, a tangent is the straight line at which, if you zoom close enough, the pixels of the straight line and the curve blend with one another. That's a loose way to say it. It's not precise, but it is gives us the idea of what's going on. So here, this is happening in 3 dimensions. So what is the osculating plane? It is the plane so that if we get close enough, if we cut this close enough, then it will seem like the curve belongs to the plane. The pixels are not, eventually are not small enough to tell the difference. Okay, so that is the idea of normal plane rather, and osculating plane. So this is the normal plane and the osculating plane of a curve. How do we find them? Okay, let's talk about for comparing purposes. So just for comparing purposes, to find a line, and that is in 2D, what do we need? We need a slope and a point. Now, so some of you will say, well, no, you need 2 points. Yeah, 2 points. And that what is the first thing we do when we have 2 points? You find the slope. So we can style the idea to slope on a point. We don't have to say 2 points, even though 2 points will do. Eventually, we have to find the slope between the 2 points and then use one of the points to come up with the equation of a line. To find, so this is one that we already know. This is from this class. To find a plane in 3D, we need a direction and a point. So we still need a point. Instead of the slope, we need a direction. The direction that we need is the direction of the normal to the plane. Whoa. So we're using normal in 3 different ways. Yeah, normal is an adjective that is used in three different ways. Let me tell you real quick before I forget. So if you got any generic plane, doesn't matter where it is, this is a bad picture. Any generic plane, there we go. The vector that is any one vector that is non-zero and perpendicular to the plane will be called normal to the plane. So this is any plane, and this vector is called normal. It doesn't matter, it doesn't have to be a unit vector, nothing. It's normal. So that's one way we use the adjective normal. If you have a curve, the vector that goes towards the center of the curvature at that one point is also called the normal vector. Normal unit vector. Okay, so those are 2 different uses of normal. But those are different uses. And then we have the normal plane. So if you have a curve that crosses a plane at a 90-degree angle, that is called the normal plane. So be aware that we're using normal for this, normal for that, and normal. We're using normal in 3 different ways. They don't necessarily, the only thing that is somewhat similar is that there's the idea of perpendicular. So this is perpendicular to the plane, this is perpendicular to the tangent, this is perpendicular to the curve. But they are different things. Do not get confused with using normal for 3 different things. So we need a direction. The direction of what? We need the direction of the normal plane. So if you have there a plane with a normal direction, let's call the direction A, B, C, and the point here, x1, y1, z1. How do we find the equation of this plane? Well, initially we can rewrite it as A, x minus x1 plus B, y minus y1 plus C, z minus z1 equals 0, because this vector is ABC minus XYZ, X1, Y1, Z1, and we want that vector to be perpendicular to any vector from here to there, which would be found by subtract. So if we have a point here, a generic point on the plane with coordinates X, Y, Z, the vector going this way would be X minus X1, Y minus Y1, Z minus Z1. This vector dotted with this vector should be 0. And that's how we end up with this equation. We can distribute the A and then move the constants to the other side of the equation. So we end up with AX plus BY plus CZ equals AX1 plus BY1 plus CZ1. And this is a constant because those are just numbers. And there's the variables X, Y, Z with their corresponding coefficients. So we typically rewrite this as AX plus BY plus CZ equals D. D is the same constant. And so there is the equation of the plane. Okay, so you need a direction and we need a point. Let's do an example. So our old example, this is going to be example 1 of this video. Okay, so find normal and osculating planes for r of t equals cosine of t, sine of t, t over 2 pi, our old friend, at, where are we going to do this? At -1, 0, 1/2. In the previous video, I mentioned that sometimes we will give you t, sometimes we will give you the point. If we give you the point, then it is your job to figure out what t is. Although we're going to piggyback on the example of the previous video, so we don't have to find t because we already found it. But if you did not know t, then it is part of your job to figure out what t is. In this case, the way to find t one way would be to match this 1/2 with this t over 2 pi. And that will directly tell us that t has to be pi in order for those two to match. Otherwise, we wouldn't be able to get 1/2 out of this if t was not if t was not pi. And then the other two fall into place. Once t is pi, then sine of pi is 0, which matches this, and cosine of pi is -1, which matches that. All right. This should go fairly fast because we are going to piggyback on our previous video. This graph is here. Remember, this is from the previous video. We have the point -1, 0, 1/2, and we're going to find the normal plane to this curve at that point. So we will have a plane like so, here, where the curve goes through the plane at a 90-degree angle, perfectly, straight on. Now, again, I'm going to piggyback on the example of previous video. In that example, we found the tangent vector. Okay, so I'm going to do, so to find the normal plane, you need a direction. The direction would be the tangent vector. So in order to find the normal plane, you need the tangent vector and the point. Add the point and the point. Yep, you need that. To find the osculating plane, okay, so we got the tangent vector, you don't need that. You have the normal vector, you don't need that. You need the one that goes away, which would be the binormal vector. So tangent vector gives you the normal vector, binormal vector gives you osculating, whoops, let me say that again. Tangent vector gives you the normal plane, binormal vector gives you osculating plane. Whoa, that's a mouthful. A third time. Tangent vector gives you the normal plane, binormal vector gives us the direction of osculating plane. Okay, so back to our example. Let's write the solution. I'm going to piggyback on the previous example. Here it is. We want the tangent. Okay, first we want to find the normal vector, rather normal plane. Finding the normal plane. You need a direction. What is the direction? The direction of the tangent vector. Now, the tangent vector is all of this. This is the unit tangent vector, but I don't need all of that because after all we need is a direction. In 2D, yeah, sorry to overlap so many papers, but I want to contrast. In 2D, if you have a slope of 150 over 50, that will work. If you want to find the equation of a line, that will do. But this is overly complicated. This is the same thing as 3, correct? A slope of 3 is 150 over 50. So why should I write this when I can simplify my life and your life by just writing 3? Even though 150 divided by 50 is equal to 3, why should we use this slope when this is just as good or better because it is simpler? Well, same thing happens here. This is a direction. What I care about this vector is the direction. I don't care about how long it is. Yes, this is the unit tangent vector, but if this by itself is simple enough, then I don't care whether this is going to be longer or shorter than just using those numbers instead. So that's what we're going to do. Neglect that, just like in 2D, neglect the 150 over 50, even though we're going to keep its value, 3. Here we're going to neglect that because all this is doing is making it longer or shorter. It's not really making a change in the direction. If there was a negative, we could still make use of that. So we're going to use only that. So the direction, we will use the normal vector to the normal plane. So you got to be careful with normal. The direction is 0, -1, 1 over 2 pi. Again, we don't need this. That is unnecessary. And the point is up here. Oh, there it is. -1, 0, 1/2. Okay, so the equation is 0 times x plus -1 times y. I guess I should be consistent, times, rather plus, direction 1/2, rather 1 over 2 pi times z equals, and then we multiply those two. 0 times -1, I'm going to write it down. down here. 0 times -1 plus -1 times 0 plus 1 over 2 pi times a half. Okay, so that vanishes. We end up with x, whoops, no x, sorry. Just -y plus 1 over 2 pi z equals 1 over 4 pi, because we multiply those two. It's handy to start with a positive coefficient on the first letter of the line. You don't have to, but I prefer not, and I prefer not to have fractions of the coefficients of the variables. So I'm going to multiply. You don't have to do this, but I think it looks neater. Multiply by -2 pi. And that way we end up with 2 pi y plus, rather, sorry to mess that up. I'm going to start it down here. So 2 pi y, we're multiplying by a negative, so that turns into minus z equals 1/2. We have a fraction here. Somebody could say, well, could we just multiply by 2? The answer is yes. If you want to go ahead, otherwise we can just leave it alone. So there's the equation of the normal plane to this curve at that one point. I just want to verify with the notes that I have written for myself. Two pi y minus, perfect, it matches. So this went fast. We still have to do the osculating plane, but I want to pause for a moment to state that this goes fast because we did piggyback on the previous video. If we did not have the previous video handy, then we would still have to go through the steps of the previous video. I'm going to show you this very quickly. There was r prime, magnitude, divide this, and then we had to plug in the t value just to get to this point. So we saved quite a bit of time by using the previous video. Just be aware of that. It goes fast once you have the direction, but sometimes finding the direction will take a little while. So now we want to finding osculating plane. We're still in example 1. So in order to find the osculating plane, we need, so there is the osculating plane. So the tangent vector goes on the same plane. The normal vector also goes on the same vector in the same plane. The osculating plane is the one that goes 90 degrees off this osculating plane. The binormal vector, rather. The binormal vector goes 90 degrees off the osculating plane. Good. So that's the vector we want to use for our direction. That binormal vector is the normal vector to the plane we are trying to find. Again, we're using normal a lot, and that can be confusing. Just keep straight which normal we are referring to each time. So again, we need a direction, which is the direction of the binormal vector. We're going to piggyback on the previous example. There it is. Oops. Couple pages over. There it is. So we have the tangent unit vector, normal unit vector, binormal unit vector. So we're going to use this direction. Now, mind, we need a direction. A direction. This is a constant. So we can disregard the constant. Use that instead. Make sure when you are doing that, you're disregarding a constant, because sometimes t is attached to this if you're doing a generic, but if you have the general formula for the binomial vector. And so in that case, you cannot neglect the t will be irrelevant. Once you plug in the t value, then things are fixed. So be aware of that. Some students make the mistake of using a variable t when they should use a constant t. Anyway, once this is constant, it's fixed, what do we care about? A direction. Remember my example. This is a slope, and so is this. Does it matter which one we use? Uh, well, it depends how you ask the question. Yes, because this is simpler, so we better use this one than that. That one is unnecessarily more complicated than it has to be, even though we end up with the same equation, the same equivalent equation, rather, an equivalent equation. So can we use all of this? Absolutely yes, but why should I make my life more complicated by keeping this constant when we can just use this direction? So 0, 1, 2 pi, 0, 1, 2 pi, and then we need a point. Well, they gave us the point in the problem at -1, 0, 1/2. -1, 0, 1/2. Okay, that's, once you have those two, then it is piece of cake. So the equation is 0x, 0x plus 1y plus 2 pi z equals, and then we multiply 0 times -1, this 0 times -1, 1 times 0 plus 1 times 0 plus 2 pi times 1/2. And then we simplify. So we end up with no x, just a y, plus 2 pi z equals 0, 0, pi. Boy, that's a very, very nice equation. So this is the equation of the osculating plane. To the curve. Let me just check something real here. So we got the normal plane was 2 pi y minus z, so no x. That means we have a y and a z relationship. Yeah. And here we don't have an x relationship either. And those two are perpendicular to one another. Yeah, so it checks out. All right, this finishes the osculating and normal planes of a curve. We'll stop here now.